So greetings. So welcome to today's class. So let me briefly recap from what we did in the previous class. So if you recall, in the previous class we were looking at like unit step response of different systems and trying to figure out like when the system response was stable and unstable, and then like we stopped with the question of what happens when a system pole lies on the imaginary axis, right?
Hello? So
Hello,
your
Manish.
screen is not visible.
Yeah, Manish, even audio is not there, right?
Yeah, audio is not there.
Okay.
I think he is trying to rejoin.
Hey, so I'm sorry, I think there was some issue. Not sure what's happening, but anyway, let me go and say start with today's session. Sorry about the perturbation in connection. So we were looking at what happens to the system stability when we have poles in the left-off complex plane and complex plane. And then I stopped with the question as to what happens when a pole lies on the j omega axis, right? So that's where we stopped. So let's try to answer that question today. I stopped with an exercise where I gave the governing equation of the second order system, and we wanted to figure out what would be the response of the system to a step input, to unit step input, and also is to a sinusoidal. So let's solve that problem today. Okay. So first, let's start from the governing equation, and then we try to figure out the transfer function. So the governing equation is y double dot t plus y dot t equal to u of t. And how do we get the transfer function? We take the Laplace transform on both sides. We take the Laplace transform, and then we apply zero initial conditions to get the transfer function. Right? So let's do it once. So if I take the Laplace transform on both sides, the Laplace of y double dot becomes s square y of s minus s times y0 minus y dot 0. So that is the Laplace transform of y double dot. Then I have y dot, the Laplace transform y dot becomes s times y of s minus y of 0. And that becomes equal to u of s. Okay, so that's what happens when I take the Laplace transform on both sides. Okay, so the next step to figure out the transfer function is apply all initial conditions to be 0, right? So let's substitute all initial conditions as 0. So, and then we will see what happens. Okay, so if we substitute all initial conditions to be 0, then we have y0 to be 0, y dot 0 to be equal Right. So sorry about that. I think there was some issue in the internet connection. I think, but I hope now you are able to hear me and hope that we can continue with our class. So as I was saying, if you take the Laplace transform on both sides and apply zero initial conditions, so this is what we get. And then what we do is that we take the ratio of the Laplace of the output to the Laplace of the input to get the Planck transfer function. So consequently, the Planck transfer function will become 1 divided by s squared plus s. I can rewrite that as 1 divided by s times s plus 1, right? So that's what would happen to the Planck transfer. Okay. Now, given that, we can immediately connect it to what we have been looking at till now. So if we look at this Planck transfer function for this system, we can immediately observe that the value of n, right, which is the denominator polynomial, is going to be equal to 2. The value of m is going to be equal to 0. And if you look at the poles, there are two poles. The poles are at 0 and -1. And there are no zeros, right? So we write the number of zeros as nil. Okay, so that's what we have. Okay, so as far as this particular system transfer function is concerned. Okay, so once again to repeat what we had been doing. So if I consider the so-called S plane and we draw the poles and zeros. So if I draw the real axis and the imaginary axis and the S plane here, so we can immediately observe that the two poles are going to be at 0 and -1. Okay, so these are the two poles. So one can immediately observe that one of the two poles is in the imaginary axis, right? It's at the origin. Okay, so now what happens? Okay, so we can see that. So what is the consequence of one pole appearing at the origin? Okay, so that is the question we need to ask ourselves and answer, right? So if we are asking ourselves this question, so let's look at the unit step response and then try to answer, right? So we were asked to calculate the output for two inputs, right? So first is for the unit step input, then for the case where the input is sine t. Okay, so first let's take u of t to be equal to 1, right? So if u of t equals 1, u of s becomes 1 by s. So by now we know what to do, right? So y of s will become equal to p of s times u of s. And p of s is anyway 1 by s plus s times s plus 1. So this becomes 1 by s squared times s plus 1, right? So the partial fraction expansion for this is a by s plus b by s squared plus c by s plus 1. Okay, so how did we get here? Because s is a repeating factor, right? So we can see that we can write s as s times s squared. In fact, if we want to go from here to here, just as an aside, I can tell you how we went from here to here. So whenever we have a what to say nth order factor in the denominator, the numerator factor in the partial fraction should be one order less. So what we have is in the numerator we can write as plus b plus a divided by a square plus c divided by s plus 1. Okay, so we can write this as in this way. Now a is by plus b by s squared, I can write in this way, right? A by s plus b by s squared, right? If I expand. So that's how we went from here to there. Okay. So I hope it is clear. All right. So now I leave the choice of calculating the residues to you as an exercise. We can get the residues for B and C very easily based on the method that we have already learned. In order to get the residue for A, you can substitute for any value of S, okay, and then get the value of the residue A. If we do the partial fraction expansion, as I mentioned, I will leave this to you as an exercise to do. So we can immediately get y of s to be the following. Okay, we can get y of s to be equal to minus 1 by s plus 1 by s squared plus 1 by s plus 1. Okay, so please try it. Okay, so if you have any questions and if you are unable to get this expansion, let me know. And we can also, I can also clarify about it, right? But by now we know how to do this, right? You have already done the homework based on it. By the way, all of you have submitted the homework. I have graded them. All of you have done it correctly, so that's good. So please keep it up and then ensure that you do all the problems correctly in the future. Okay. So if I take the inverse Laplace transform, this is what we get, right? So the inverse Laplace transform of minus 1 by s is minus 1. The inverse Laplace transform of 1 by s plus 1 is e power minus t. Now the inverse Laplace transform of 1 by s squared is t. So now one may ask, what is the consequence, right? So we can immediately observe that due to the presence of the t term in the response, we can observe that as time t tends to infinity, the magnitude of the output tends to infinity, right? So we can immediately observe that, we are giving a bounded step input, but the output is unbounded in magnitude, right? So that seems to violate the definition of Bigot stability, right? See, what was the definition of bounded input, bounded output stability? The output of the system should remain bounded for all possible bounded inputs and for all time, right? So that was the definition of the Bigot stability. But in this case, we saw one input, which is a bounded input, the step input, but then the corresponding output was unbounded, right? So consequently, we can see that the definition is violated. Then we ask ourselves the question, right? Does this mean, does this imply or mean that this system is unstable? Okay, so that is a natural question to ask ourselves, right? So essentially, we can ask ourselves this question, and then let's try to answer it by figuring out the output of the system when u of t is sine t. Okay, so please remember, what are we trying to do? We are trying to essentially get the what to say, output of the system when we are having the unit step input and when we are having a sinusoidal, right? So that is what we are trying to do now, right? So let's try this example, right? And then let's see what happens. Okay. So if u of t is sine t, if we consider u of s will become 1 by s squared plus 1. Okay, so that's what happens with u of s. Okay, so u of s becomes 1 by s squared plus 1. Then what do we have? We have y of s to be equal to p of s times u of s. Okay, and that becomes 1 divided by p of s was 1 by s times s plus 1. And then we have a squared plus 1 factor coming in additionally now, right? So once we have this, we have partial fraction expansion as a by s plus b by s plus 1 plus cs plus d divided by s squared plus 1. Okay, so that's what happens to a partial fraction expansion. Okay. So now the question becomes, how do we do this, right? So by now all of us know, right? Let me do this partial fraction expansion so that we can ensure that all of us are on the same page. So in order to find a, what do? We multiply both sides by s and substitute s equals 0, right? If I do that, I will get a to be 1. Okay, so because other terms on the right hand side will become 0, the s in the denominator of the left hand side will cancel off, and then I can substitute s equals 0. Now, if I want to find b, I multiply both sides by s plus 1 and substitute s equals minus 1. If I do that, I will get b to be minus 1 by 2, right? So that's what will happen with b, right? So because you can observe that on the left hand side, the s plus 1 will vanish in the denominator. If I substitute s equals minus 1, I will get b to be minus 1 by 2. Okay. And then the question remains, how do I find c and d? Okay, because I have to essentially get the residue c and d to complete the partial fraction expansion, right? So one can do it in multiple ways. Please note that this equation has to be satisfied for all values of s. So let us substitute any two values of s, okay, which we have already not considered. We have already substituted s equals 0 and s equals minus 1, right? Now let's say we substitute s equals 1. If I substitute s equals 1, what I need to do is that I need to substitute s equals 1 here and s equals 1 in this right hand side, right, of this equation, right? So that those are the two places where I need to substitute s equals 1, and then we need to see what result we get. Okay, so if I do that, what do I get? You know, like on the left hand side, I will get 1 by 4, and on the right hand side, I will get 1 minus 1 by 4 plus c plus d divided by 2. Okay, so this is what we will get. So this will imply that c plus d will become equal to minus 2. Okay, so this is the first equation I will get relating c and d. Okay. Now we, of course, we have two unknowns, right? So we need two equations. So let's substitute, let's say s equals 2. Okay, some other value of this. So if I do that on the left hand side, what will I get? If you do the math, you will see that the left hand side will become 1 by 30. Okay, so I hope I'm correct. So please correct me if there is an error. So this will become 1 by 30. 1 by s will become 1 by 2. Minus 1 by 2s plus 1 will become minus 1 by 6. And then cs plus d will become 2c plus d divided by s squared plus 1 will now become 5. Sorry. Okay, so the denominator here will become 5. So if I now process this equation, I will get 2c plus d equal to minus 3 by 2. Okay, so now I have two equations, right? So c plus d equals minus 1. And 2c plus d equals minus 3 by 2. If I simplify and solve these two equations for c and d, we will get c to be minus 1 by 2, d to be minus 1. I'm sure this you can do this. I am going to leave this as an exercise to you. Okay, so essentially this is what we will get. Okay, so then we substitute in the expression for y of s. So what will the partial fraction expansion look like? We have 1 by s. And then like minus 1 by 2 times s plus 1. These are the two terms we are already aware of. Then cs plus d, both c and d are minus 1 by 2. Sorry. Yeah, both c and d are minus 1 by 2. So what we are going to get is the following. We will get minus 1 by 2 times s divided by s squared plus 1. I'm writing it in this form and just splitting them. And then we also have minus 1 by 2 divided by 1 divided by s squared plus 1, right? So this is the next step. So if we take the now the inverse Laplace transform, we will see that the output y of t will become 1 minus 1 by 2 e power minus t minus 1 by 2 cos t, because the Laplace inverse of s divided by s squared plus 1 is cos t. And then like minus 1 by 2 sine t, because the Laplace of 1 divided by s squared plus 1 is sine t. So this is what I will have, right? So essentially, this is the output function. Okay, so this essentially shows us that y of t is bounded in magnitude. Correct? So we can observe that as t tends to infinity, yes, it's going to oscillate, but it's not going to blow up to infinity, right? So that's something we essentially need to do. this symbol means for all. Okay, so if I put a D with a horizontal line, that means for all. Okay, that's what is the meaning. So we can observe that from this exercise, the magnitude of the output function y of t is bounded when we are giving a sinusoidal input, right? Whereas it was unbounded, right? When we gave a step input, right, to the system. So this sounds very puzzling, right? So because we have a case where we have a pole at the origin on the imaginary axis, and we give a step input which is bounded in magnitude, but the output is unbounded. On the other hand, we give a sinusoidal input, which is also a bounded input, but then the output is now bounded, right? So one wonders, like what one can conclude from it. Okay. So I am going to essentially now write certain conclusions, okay, based on these examples. Okay, so not the best way to do things. Like typically what does in a theory course, in a control theory course, is to derive this mathematically and do it. But ours is an applied course, right? So what we are going to do is only use the results. So consequently, what I am going to do is essentially write down the final what to say results, right? So that's what we are interested. So if we note the following points, right? All poles lie in the left of plane. Okay, so if we have scenarios where all the poles lie in the left of plane, this implies Bigot stability. Okay? So I'm just summarizing all the main points. Okay, like how do I what to say connect Bigot stability to the location of poles of the transfer function? So what essentially we have is that, like, if all the poles of my transfer function lie in the left of complex plane, my system is Bigot stable. Okay? So if even one pole, yeah, of the system transfer function lies in the RHP with all remaining poles in the LHP. Okay, system is unstable. Okay, so it doesn't matter. Okay, so even if what to say, there's only one pole in the right of complex plane, and one may say, hey, all the other poles are in the left of complex plane, but still the system is unstable. Okay, so let me put this in parenthesis because this is a secondary argument. The main argument is even one pole in the right of plane. Okay, it doesn't matter where the remaining poles are. Okay, so that is what I want to look at. Essentially imply here or reiterate. But the another main consequence is that, like, the system output will be unbounded for all bounded inputs in the space. Okay, so this is very important. Okay, the keyword here is all. Okay, so for all bounded inputs, the system output will now become unbounded. Okay, so that is the key fact here. Right, so when we have even one pole in the right of complex plane. Now let me write down other cases, right, based on today's example. Okay, so if we have non-repeating poles, okay, what are called simple poles. Okay, so poles which don't repeat, okay, or what are called simple poles. Okay, on the j omega axis, on the imaginary axis, with no poles in RHP. This would imply that system output is unbounded only for select inputs. Okay, so that is the consequence. Only for selected inputs, the system output will become unbounded. Okay, so if you have non-repeating poles on the imaginary axis, like what we had in that example, right? So we had a pole at s equals 0, that is at the origin, and that was not repeating, right? So if you had such a pole, what happens is the system output will be unbounded only for select inputs. So in our example, the system output was unbounded only for the step input, right? But for all other bounded inputs, like sinusoids, it will become bounded, right? So for this reason, some people will call it as marginally or critically stable. It's not stable. Okay, let me be very clear. Okay, so this is a very tricky statement. Okay, you call it as marginally or critically stable. Uh, if one were to follow the definition of stability very, very strictly, I can also ask ourselves the question: should we call it as unstable? Okay, see, in the previous case, when there was one pole in the right of plane, the system becomes unstable. That is, the system output is unbounded for all bounded inputs. Okay, but when we have non-repeating poles on the imaginary axis with no pole in the right of plane, the system output is unbounded only for selected bounded inputs. Okay, not for all bounded inputs. So this sort of looks like a different case, right? So than the previous one. Okay, so that is why like people call this as a uh, marginally stable case or a critically stable case. Okay, so it's not exactly what to say unstable or unbounded. Output is not unbounded for all bounded inputs, but only for selected inputs. But then, if one were to strictly apply the definition of stability, see what was before stability? The system output should be bounded for all possible, all bounded inputs and for all time, right? So that's what we wrote down. So if you recall this definition of stability that we wrote down, so if you look at the phrases which I have underlined in red, right? So the key phrase is all bounded inputs, right? So it doesn't matter, like whether it is one or every, right? So it is unstable, right? If the output is unbounded. So, but then, like in the literature, people have a sort of like two views on it. So that is why I'm presenting both. You can adopt whatever you feel is appropriate. Okay, so in this particular case, okay. So now there is a fourth case when there are repeating poles on the j omega axis. Suppose let's say there are two poles at the origin. It can happen. Okay, so let's say there are repeating poles on the j omega axis. And no poles in the RHP, what happens? Okay, when there are repeating poles on the j omega axis with no poles in the right of complex plane, what do we get? Okay, so in this particular case, one can show that it's unstable straight away, and the output is unbounded for all possible bounded inputs. Okay, so one can notice the subtle difference, okay, between case 3 and case 4. Okay, so output becomes unbounded for all bounded inputs. Right, so that is the difference. So in case 3, the output was unbounded only for selected bounded inputs, right? So in case 2 and case 4, if we encounter such cases, the system output becomes unbounded for all bounded inputs, whereas in case 3, only for selected bounded inputs. Okay, so these are important, what to say, facts, okay, that we need to remember. So some people, main thing which we need to remember is that like for pivot stability, we need all poles to be lying to the left of complex plane. And we will later see that when we go to what to say, automotive control, the criteria for so-called asymptotic stability of this class of systems is also the same. Okay, so these two terms are used interchangeably. Right now, I just want to alert you regarding that. But then like this is because when all poles lie in the left of plane, some people will call the system as asymptotically stable. Okay, so please keep that in mind. We will see what that means later, right? So when we essentially go to advanced courses in automotive. Okay, fine. So let me carry on. Like sorry once again today. Like due to some reason, speaker is not working with Linux, so I am unable to hear you even if you have a question. But if you have a question, please do type in the chat box. Okay, like and then I will answer that. Okay, so sorry about the inconvenience, right? So, all right. So now just expanding a little bit of case 3. Okay, so I just want to essentially write there is 2 parts to case 3. Okay, so if we have a non-repeating pole at s equals 0, which is the origin in the complex plane, what happens with no poles in RHP? So what happens is the following. Okay, the system output is unbounded only for a step in. So we saw that when we have non-repeating poles on the j omega axis, the system output is unbounded only for selected inputs, right? So it so turns out that when we have a non-repeating pole at the origin at s equals 0, the system output is unbounded only for a step input. We already saw that, right? That was the example. Okay. Now, similarly, when we have a non-repeating poles at plus or minus j omega, we are going to see an example as to how this can occur. Okay, this is on the j omega axis. Okay, omega being not equal to 0. Okay, with no poles in RHP, what happens? Okay, like for what class of system inputs will the output become infinity? So in this particular case, the output is unbounded only for sinusoidal inputs like sine and cos, right? Sinusoidal inputs having an angular frequency of omega. So this is very important. Okay, so angular frequency of omega. Okay, so what do I mean by that? If the input is, let's say, sine omega t or cos omega t, okay, the output will become unbounded. Okay, so that's the implication. Okay, so when we have say we have non-repeating poles at plus or minus j omega. Okay, so that is what. All right. Okay. So now one important comment, like before we go further, and then like do an example is the following. Okay. So what is this comment? Please note that like in this particular course, we are dealing with systems whose governing equations are going to be by and large linear ODEs with constant coefficients, right, for the purpose of analysis. And when we take the transfer function, we are going to get polynomials. Yes, this is a complex variable, but they are called as real polynomials in the sense that they are polynomials with real coefficients. See, for example, like when we looked at this particular polynomial, right? So yeah, if you look at the transfer function, right? So we see that we have s divided s times s plus 1, right? That is s squared plus s. We can see that that's a second order polynomial, and the coefficients are all real. Okay, so if you look at the denominator polynomial, it is s squared plus s. It is a second order polynomial, and the coefficients are 1 and 1, right? Coefficient of s squared is 1, the coefficient of s is also. Okay, so we are dealing with what are called polynomials with real coefficients. Okay, So this is very important for us to remember. So I'm sure all of us would have learned it. I'm only reiterating these results. For polynomials with real coefficients, okay, complex roots, if they exist, okay, if they exist, okay, exist as conjugate pairs. So what do I mean by that? If we can have complex roots for polynomials with real coefficients, but then they should occur as conjugate pairs. So what do I mean by that is, if, for example, we have sigma plus j omega as a root, then sigma minus j omega also should be a root. Okay, so let's take an example. I'm sure you can look at this. Suppose if we had some polynomial as s squared plus 2s plus 2, right? You can solve and convince yourself that the two roots are going to be -1 plus or minus j. Okay, so please do that as an exercise. It's a pretty straightforward. So bottom line is that, like, we can see that this is a polynomial with a real coefficient, right? And we essentially have what to say, a complex conjugate pair, right? As its roots. Okay, so that's what, right? So that's very important for us to remember. Okay, so this brings us to homework number 2. Okay, so I'm now going to pose problems for homework number 2. So essentially, I'm going to give you an exercise problem to begin with. I will solve the initial part, and then I will tell you what the homework is. Okay, so consider a system whose governing equation is the following. This governing equation is y double dot t plus y of t is equal to u of t. Okay, so that is our governing equation. Okay, so of course, the first part is find its transfer function. Let's say we take, let me do it one more time. So let's say we take the Laplace transform on both sides. We take the Laplace transform on both sides. What we are going to get is we will get s squared y of s minus s times y0 minus y dot 0 plus y of s is going to be equal to u. Okay, so that's what we have. And then let's say we apply 0 initial conditions. Apply 0 initial conditions. So what do we get? We'll get s squared plus 1 y of s will be equal to u of s, right? So that's what. Okay. So if we have this, now what can we conclude from here? From here we can conclude that the Planck transfer function, which is y of s divided by u of s, is going to be equal to 1 divided by s squared plus 1. Okay, so that is our system or Planck transfer function. Okay, so that's what. Okay, I'm sure these steps are clear to everybody. Okay, so this is straightforward. So now, so having obtained this, we can immediately see that the value of n is 2, the value of n is 0. The poles are going to be obtained by solving the denominator polynomial equals 0. Right? So this is like s squared plus 1 equals 0. Right? So this implies that s squared equals -1. So this implies that the poles are going to be equal to plus or minus j. So we can see that we are having poles on the imaginary axis, right? Non-repeating. Okay, so there is only one pole at plus j, one pole at minus j. Okay, so that's what we have. And then if we look at the zeros, obviously in this example also there are no zeros. Okay, so essentially, let's say we draw the S plane. Okay, so what we are going to have is the following. We are going to have a pole at plus j, pole at minus j. Okay, so that's what we are doing. Okay, so I'm sure it's clear to all of us. So now I'm posing the homework questions. Okay, so of course, this is part of homework number 2. Okay, so this is part of homework number 2. Of course, I solved the initial part for you. So this is the first problem of homework number 2. So what I want you to do is that like find y of t. I have already derived the transfer function, right? So please find y of t for 2 inputs. Okay, first u of t to be equal to 1. Second, u of t to be equal to cos t. Okay, so these are the 2 inputs for which I want you to find and then comment. Okay, so please, I will tell you the answer a priori based on the result that we wrote down, right? As condition, what to say, 3, right? And the 2 subconditions. So here the poles are at plus or minus j, right? So the value of omega is equal to 1, right? So obviously for the step input, you will get a bounded input, sorry, bounded output. However, for cos t, the angular frequency is equal to the magnitude of the pole, right? You will see that the output will become unbounded. Okay, so essentially find and then state your observations. So I have already told you what your observations should be. So you just do the problem and ensure that you are getting the same observations. Okay, so that is the first one. Okay, the second problem, I am going to give you another exercise wherein we consider a system whose a second order system once again, whose governing equation is y double dot t plus 3y dot t plus y of t is equal to u dot of t plus 3u of t. Okay, so we have already considered a system whose governing equation is y double dot t plus 3y dot t plus 2 y of t equal to u of t. That is, the right hand side was just u of t. Okay, but now I have modified the right hand side. Okay, so you will see that when you take the Laplace transform, you will see you will observe a 0 coming into picture. Okay, so please calculate that very carefully. All right. So what I want you to do is that derive the transfer function. Okay, and calculate the unit step response. And state your observations. Of course, you have to compare it with what we got previously, right? So when we just add y double dot t plus 3y dot t plus 2y of t equals to u of t. Oh, sorry, I think I made a mistake here. This should be y of t. Oh, sorry, this should be 2y of t. Sorry. Sorry, okay. Please change it. Like on the left hand side, the governing equation should be y double dot of t plus 3y dot of t plus 2y of t equals u dot t plus 3. Okay, so please change that. So we have already done the problem where we solved y double dot of t plus 3y dot of t plus 2y of t is equal to u of t. Okay, so we have already done the problem and calculated the unit step response. Now solve this problem. Okay, I have only introduced a 0 on the right answer, right? So now find the unit step response and then compare it. So you will observe that still you will have exponential terms. The poles will still be the exponents of the exponential terms, but then the effect of the 0 will be that the residues or the coefficients that multiply the exponential terms will be changed, and also the steady state value of the output will be changed. Okay, so that will be the impact. But please figure it out for us. All right. So please do these 2 problems. Okay. So let me stop here for today. We have looked at stability and criteria for stability and few special cases associated with that. So are there any questions? So once again, if you have any questions, please type them in the chat box. All right. So if there are no questions, let me stop the recording. Thank you.